Okay, so we're very happy to have Arijit Ghosh, Professor Arijit Ghosh from ISI with us. Yeah, Arijit works on a wide variety of things, but all around, I think, some theme of geometry, combinatorial, discrete, computational. And he has other interests in works in Boolean function analysis and many other things. So he's going to talk about colorful extensions of. You won't say how people are also taking up you as a geometry. Oh, right. That's what I mean. So somebody remarked to me, I never knew that you work in geometry. And I said, no, I don't. And I said, but no, some colorful people. And so unknown to me, the notice carried that the organizer was me. So I was completely. It's best
Thank you for inviting me. So I was like standing in front of the window. I saw the weather outside. I'm very sorry to give you this room now. But, okay, so we have any questions. More appropriate I would be just infinite PQ theorems in computational geometry. So this is like a recent set of results that have come up, and I want to introduce the topic and what are the results one can prove. So first, I want to introduce what is PQ theorems in computational geometry. I'm sure many already know, but just so everyone is on the same page. And then I will show what are the infinite PQ theorems again. Good. So if you have questions, please don't hesitate to ask. Okay. So well, it's a joint work with two PhD students in ISI Kolkata, Shutana Chakraborty and Shomi Namji, and the results are there. Really, I'm just like an ad agency person coming, not that involved with the product, but like to say the product is okay. Okay. So these are the main people who work on this project. At the same time that they have started working on this problem, there's another group in Budapest who was also looking at this version. So, and since Jung and Pavel were also looking at this problem, and they got similar results, but with completely different techniques, which is interesting. So I want to like mention that most of the results that I will be presenting as are also like they are also have similar results, if not same. So let's start with what is Helly's theorem. Okay, so let's say Helly's theorem in R3. Okay, so it's about you have some collection of convex sets. Okay, so for the time let's assume the convex sets are compact convex sets. Okay, so if you don't know what compact convex sets are, so nothing to worry. So the convex sets that you can draw on paper are compact. It's very difficult to draw non-compact convex sets on paper and pencil and paper. Okay, so. And now you want to know whether there exists a point that lies in all of them. So one natural thing to check is like go through, like keep intersecting one by one, and once you get like an empty set, then you know there is no point. If you intersect all of them, finally you have a non-empty set design, then obviously you know like okay, there is a point. But can there be a simpler test for it? Okay, and by the way, if your convex sets are, if your family is finite, then you can just write a linear program and so. Simple linear program. It's all. Okay. And sets doesn't have to be, by the way. So with the version of Statistical that I will be mentioning, the set doesn't have to be polytops. Even then you will do it. Okay, good. So let's see. What is a Helly's criteria? So Helly's theorem is more than 100 years old now. It basically says that if your collection of convex sets satisfies the following property, that you take any three of them, I'm talking about everything in R2. Okay? I will tell you what the version is in R2. If you take any three of them, this family, the collection of convex sets in R2, if they have a non-empty intersection, then the whole family have a non-empty intersection. So let's say I've given one triplet, and they have a hopefully they have a non-empty intersection. Okay, and this is one, but there are like n choose 3 many. If all of them have non-empty intersection, then the whole family has a non-empty. Nice. It's an if and only statement, right? So, so how does it go for like RD? So RD the criteria becomes. So again, you have same thing. You have a collection of convex sets in RD. You want to know. You want a criteria that tells you that okay, this family has a non-empty intersection. So what you do is you take any you check all t plus 1 tuples. Okay? And for any d plus 1 set, if they have a non-empty intersection, if all of them have a non-empty intersection, all these d plus 1 tuples, then the whole family has a common point. Like there's a point that lies in all of the convex sets. Okay? Does make sense? Good. The family, by the way, doesn't have to be finite. The collection. Okay? The collection can be an arbitrary collection, but if you work with arbitrary collection, you want this sets to be compact.
What is this set to be?
The sets, the convex sets inside your family has to be compact. Okay. But if it is finite, then it doesn't have to be compact.
Close is not good enough.
Yeah. No, close is not good enough. And one second write in code here.
Yeah.
So one thing to see is, let's say your sets are SIs are of the form all x, okay, greater than or equal to, let's say 1. So SI will be pi. Okay. So these are the collection of sets that you like, collection of x's you're looking at, and SIs are like those. Okay. And like these are all objects in R. Okay. So any two are intersecting for the whole family. And they are close sets. Okay. And similarly, you can do for like the is let me relax the condition that can open sets, infinite collection, open sets can have each other mode. You can do the similar thing. You can look at, let's say all similarly you can define, let's say SIs, SI primes to be all, let's say x between all x between 0 and let's say 1 by 2 pi. Okay. And let's say your I goes from 1 to 2. Okay. Again, there is conditions to satisfy, but there is no point that lies in it. And this example kind of tell you why you need actually. So, well, this is very simple. Tells you why you need it.
Can you still find the intersection in polynomial time in large dimension?
In large.
So the dimension D is, let's say, very large compared to N.
Yeah, so one thing you can do is okay, so let's do the simple case. Okay. So let's say they are all polygons. Okay. So if they are all polygons, so they will be defined by intersection of half spaces. So let's say each of them are like, so A1 you require T1 many half spaces to define, A2, T2 many. So this boils down to finding intersection of like half spaces, number of half spaces in the radius, summation Tx, and the termination will be. Is that it? But then you are solving linear programming diagrams. If D is constant, there are fast algorithms. I mean, there are fast algorithms solving linear programming. I don't know if they are not, but like for D, you can get linear in N actually. Linear in number of things.
But there would be some dependence on bit length also.
Yes, that is there also. Yeah. So here I'm assuming like representation size is 9 something. Any bottleneck that is there for linear program will be here. It's those you cannot get away.
Is this simpler than just checking if taking all the constraints together and checking if they're feasible? Because that would be the intersection level.
Yeah. So this So this easier, so these problems came out in the sense of, so let's say finding intersection, let's say you're working with, let's just you're working with very simple object, let's say closed balls, okay, in very high dimension, so D is large, okay, and the number of closed balls are also, like keeping track of intersection of closed balls is a complicated algebraic thing. It becomes it becomes hard to implement with floating point algebra. But let's say if you're okay with doing it for n plus one of them, then you check all n plus one doubles, check whether they're
D plus one.
yeah, or d plus one doubles, then you will be done. Yeah, okay, so now there was like a more general version that was proved by Lovers. So that goes in the following way. So let's say you have D plus one families. Okay. So each of them are collection of convex sets in R. Okay. And this family satisfies the following property that if I take any set from F1, let's call it C1, anyone from F2, C2, dot, from Fi, I take Cj, D plus 1, Cb plus 1. These things will have a point in common, they will intersect. Okay. Let's call it a colorful tuple. Okay. By colorful means I'm taking a D plus 1 convex sets from these collection where each of them come from a different one. Okay. And suppose this property is there that all colorful tuples are X. Okay. Then what colorful Helly theorem says is, so there will exist one, so it says that there will exist one Fj, okay, which has a which can be intersect, all the convex sets here can be intersected with one. So basically they have a non-empty intersection. If all colorful D plus tuples are non-intersecting,
Yeah.
then you will find a J between 1 to D plus 1.
Right.
So this family can be hit with 1 point. But if I take intersection of all the convex sets in this family, okay, it is 1. Okay.
So you have the collection of convex sets and you are making families out of that and you are
Okay. So you have D plus 1 collection. Each of them, each Fi is a collection of convex sets. Okay. The convex sets from R.
How is this? I mean, there's something I'm missing. Like, if F1 just consists of, let's say, a huge, like F1 and F3 are huge balls, whereas Fj consists of disjoint sets. Oh, you're seeing one of these. Okay.
At least. Okay. So now, see the level is even slightly more impressive than what I have mentioned. Yeah. So here I'm assuming.
Why is it the generalization of
we take all FIs to
So you can take each Fi to be single. So by the way, it says something even more, which is interesting, and it's never written in like the literature, but it's implicit in the proof. The only proof I could find is Barney's paper from like something called colorful gatherer theorem. This one is there. Mainstream lower again. Some different point. Okay. So if you go through the proof, what actually says is something even strong. So let's say you have now collection of n collection of convex sets. Each of them are collection of convex sets from R. Okay. And n is greater than or equal to D plus. Now what you want is, what property does this collection satisfy? The property satisfies is, if I take D plus 1 convex sets from this union in such a way that each of the convex sets come from a separate term. Okay. You get it? So you will you choose D plus 1 of this and take one from each. Okay. Anyway, you choose D plus 1, take one from each of them. Okay. And they will be intersect. Doesn't matter which one you choose, internally which one you choose also. Okay. If this is true, okay, then there exists a point P in Rp, okay, such that P will be hitting set for at least n minus d many families. N minus d, I'm just write it there, many families.
You can use the buttons to move.
Oh. But that it will go up.
No,
Just these buttons. Oh, then the red one. Yeah. It's kind of interesting, it doesn't have to be deep, doesn't mean it's even more. And then, like, I'm not even saying that all these n minus d have a, like, each of these families have a non-empty intersection. If I take the intersection of the convex set in all of these families, they're non-empty. No. You can take the union of all the convex sets in these n minus d families. Okay. They will have a okay, so here like a very simple example. So like there are three colors. So black. So let's say one family is all the contains all the convex sets whose boundaries are black. The second family, all the convex sets boundaries are red. Blue is the one with all the convex sets with boundaries blue. Take any colorful three tuple, they're intersecting. Okay, then it says at least statement that I've mentioned here, at least one will be there, which if I take the intersection of the convexes, non-empty. Only problem is actually if I take intersection, all of them it's the same exactly. Yeah, that's not a very good example, but the idea I should have like fixed it in itself. But, yeah. Okay, so what we are interested is so here the thing is the way to think about Theorems one of the ways hitting set kind of a framework. Okay, so if some Helly property is satisfied, let's call that D plus one property Helly property, whether it's colorful or not, in its own statement. Okay, and then I can hit the whole family, right? Or there will be n minus d families will be that can be hit with one. Okay, and so rather than calling it hitting, we call normally people like to call it transversals. Okay, so in combinatorial geometry, there is sound important maybe, but hitting is as natural. But okay, so what we will be interested in this talk is not just points, but hitting with higher objects. In the sense, let's say lines. So you have some collection of convex sets. Let's say R3, it satisfies some property, very like local kind of a property satisfied. Okay, if this property is satisfied, I want to say, okay, this is the whole family can be hit with 4 lines. Okay, and something like this I want to do. Okay, so let's just formally define it. So let's say you have a collection of sets from RT, and tau is also a collection of let's say call it geometric objects. So tau you should think of as point, either there are points, lines, affine spaces of dimension k, let's say, okay, something like this. Okay. When I say tau is a transversal of f, if for every f in every small f in this capital F, there exists a set in tau such that that set intersection f is on.
So F is a set. F is some kind of a set in RT.
Which one? Small f. The non-mathcal f is a set in. Okay.
And we assume it's convex.
For the time, let's not assume anything. We will, when we prove theorems, we will all impose. For the time, this definition doesn't need any conversely. But like, when you keep in mind, as I've already mentioned this, I want to keep it as general as possible, but ideally I want to keep this as affine spaces.
But T is also a set. Why? What is the geometric object? What is
Yeah, so you should think, okay, yeah. So here, let's say, one of the things here, ideally you just want F to be, let's say, connected sets, compact connected sets. And shape is not something I want to restrict.
Okay.
Tau is a collection of also sets, but think of them as macro structures, they're points, or it's a collection of lines, it's a collection of two-dimensional affine spaces in, let's say, R4, things like this.
But sorry, so you're not imposing any restriction on the size of the family tau, right?
Yes, for the time being, let's not.
No, but then why it couldn't be like, why shouldn't it be now a trivial thing? Because
Yeah.
for every F in F you have.
See, I'm not making any statement about theorem. This is just a definition.
Or is it a template?
Yeah, template. Yeah, I mean, there's obviously a trivial hitting set of size m for m sets.
Yeah.
It's like,
Yeah, so from the definition, I feel that if tau is not a singleton set like a point, if it collects the two different points, so it might happen that for some part of the family, member of the family, the point one will satisfy, but for someone for point two.
yeah, it can be the case. So it may be the case. So let's say tau has 2 points.
Yes.
And the first point hits some subset of F,
Yes.
and the second one hits the other one.
Yeah, so that for a singleton set tau, it has statement is stronger that you mentioned in the release.
Yeah, up till now I'm not making any statement in terms of theorem. Just the definition. So I say tau is a transversal. That's it. So I'm not making any like if this is true, then there is a something.
Transversal and piercing also.
Yeah, this is again something. I personally prefer piercing more, but so it's like a line. And the thing is, it is like think of it as a line going through a set. Okay. So let's see this object. So we have this collection of, let's say, green circles. Basically.
So this is a
Like interior empty. Think of them interior empty also. Not even think don't have things also.
These green circles are the S.
Here, okay. And what you want is now, and tau is basically your this three lines, blue lines. Okay. And what you can see is these three lines intersect all of them. Right? If you take any one, I will find a line that goes through. So these blue lines are a transversal of these green circles.
Your tau is the collection of all triples of 9.
No, just
three lines.
just these,
So you're covering the.
just these three lines. So, so one thing thing that I said, like, if I want to define what is a PQ theorem, so for that I need to define what's a PQ property. Okay. So let's say we have a collection of subsets of RD, okay, and you again have this collection of geometric objects, okay, and I say F satisfies PQ property with respect to tau if I take any P sets from F. Out of these P sets, I will find Q sets that can be transversed by a single geometric object group. Okay, take any P sets, okay, from F, you will find Q out of this P that can be like transversed by a line. Let's say tau was a collection of lines, some set of finite set of lines. Let's say. Then this Q can be transversed by.
So this is exactly like Helly.
Slightly relaxed, right? So if I want to define Helly, how will Helly look? So a Helly property, let's say if I want to define Helly property will be your tau will be all of RT, okay? F will be some collection of convex sets, okay? And I will say it satisfies Helly's property, which is equivalent to saying it satisfies D plus 1, comma D plus 1 with respect to this all points in it. So again, like the interesting cases are like basically when F is a collection of compact convex sets in RD again, and suppose, and let's say your tau is collection of all points in it. Okay. Let's say F satisfies PQ property with respect to points. Okay. So what Hadwiger and Tribunal asked is, so suppose
Where are these points? Oh, points are just in some points in RD.
yeah, all of it. For this theorem, the thing of it is all points in RD. And he's asking the following question. Okay, we have F. Okay, and F satisfies PQ property, where P is greater than equal to Q has to be that, and you want Q to be at least D plus. By the way, Kelly's theorem, when we say that D plus 1 intersecting, that is style, we cannot make it D. Okay. You can have, let's say, it's not orthogonal, there is pairwise intersection in R3, but the whole family cannot be. Okay. Good. So now what we want is, what they ask is for all P and Q satisfying this, does there exist a constant that depends on just P, Q, and D, such that if F satisfies PQ property with respect to points, then there exists a transversal of F, point transversal of F of size at most C, P, Q, D. Okay, a constant that just depends on P, Q, and D. Okay. They proved a special version of this theorem. Okay.
A bit like Ramsey kind of thing, right?
Kind of. Okay. So it will come more naturally. Yeah. So these are sometimes this area is also called like an extremal combinatorial geometry. So they are like very closely connected. And by the way, like many tools from like graph theory tools for Ramsey theory comes and plays a role. So it goes like. Okay, good. So they prove it, but I have forgotten the bound actually. So they prove for some values of P and Q, okay, like if PQ satisfies some relation more than this, okay, then it is true, they showed. And that was the generalization of Ellis. So from that you could have got Ellis theorem by just setting P equal to D plus 1, Q equals to D plus 1. Okay, you won't get the whole of Ellis theorem. You will actually get its P minus, you get the whole of Ellis theorem. Okay, so the condition on P and Q I forgot, but if I remember, they showed there exists a transversal of size something like P minus Q plus 1.
So what is varying this? The content of this is that the dependence of the size of the transversal is on the component.
No, it does not depend on the family. Just depends on P.
So for D equals 2, if I said D equals 2 and PQ equals 3, then this would mean that I have to find a constant set of points which hits every family.
Yeah.
No, for that, every family has some set.
Yes.
So for every family there's a constant size.
So the Ellis theorem is P equal to D plus Q equal to D plus 1.
Yeah,
And C P Q D is 1.
1.
C P plus 1, D plus 1.
Oh, I see. Given a family of, yeah, okay, thank you. Okay, thank you. Yeah.
And that shows that P minus Q plus 1 is typed from Ellis.
Yeah, so for particular range of P and Q, the condition which is, they needed one additional condition other than this one. And for that, you get this. Their theorem was actually, from their theorem, you could have, like, it's a generalization of Ellis. So, Ellis theorem follows as a corollary, which is setting P, D, same as this. Okay. And what they ask is like for all PQ, this should be. Yeah, it was very like an active area.
They proved it, aren't you saying? Or is this a conjecture? Sorry,
No, so they proved this bound. So they proved C, P, Q, D is P minus Q plus 1 if an additional property is satisfied, not just this one.
Oh, you haven't said.
Yeah, that are not written in rules. But the additional property, the only thing to one main take home is it takes care of this. Using their condition,
You can still derive this.
Ellis.
Nice.
But it's not for all PQ.
Is it for infinitely many? Or is it for infinitely many PQD?
Yeah. any PQD that satisfies this
No, the extra property.
infinitely many, so like, yeah, so but then you just can like there are infinite family, because you see, Helix theorem satisfies for all D, right?
Yeah.
So this will be.
No, I think you're saying that what they could prove was such PQ sets with some additional property will have that, right?
Right. So I'm like this property, F satisfies, like P is this, so condition on PQ is just this, right? Both have to be like P has to be greater than Q and P plus one, and F is your satisfies PQ property. Okay, they just this they could not prove. You bring in some more conditions that P and Q has to be satisfied, and D, okay. Then they could prove that comes out to be this.
Oh, so the condition was just on some relation between PQ and D. I see.
And that takes care of, like, even though their result is not for all PQD greater than equal to D plus 1, okay, still takes care of Helix theorem. It takes care of electron. Get Helix theorem as a called. Okay. So, we're close to like 35 years later, like Alon and Triton actually resolved. Okay. So, they showed that there exists a constant, okay, that depends on PQD. So their problem is, yeah, there does exist a constant, okay, and any family that satisfies PQ property can be hit with C of PQD many ones. And so this has been really an active area of research and has been studied from many angles.
How bad is this?
Very, very bad. Okay, they did not try to optimize. This the one thing that has been done is trying to improve this bound for particular families. Particular families is one important family is what are called rectangles. So family of let's say rectangles in R2 itself. Okay, you could improve this bound quite. Okay. And you could there's some other things are also beside. So now, so again, if you look at Ellis theorems, Ellis proof, you could actually see that it doesn't just hold for convex sets, but for slightly more general objects. Okay, so contractible sets. So if you don't know, doesn't matter. Some more complicated objects also it holds. Still nice. Okay, but some more complicated objects also it holds. So that also has been like explored for these problems. Okay, so your family is not just convexes, but some collection of sets that satisfy some nice topological properties. Okay, and then you want to understand what this behavior is. Now, finally, we are far from the really pinning down this. So soon after, like Helix theorem was proved, like PQ theorem, like Alon's PQ theorem came in, like Alon and Kalai actually showed that we have a PQ theorem for hyperplanes. Okay, so in the sense, like again, PQD satisfies this property. Okay, and now your tau is collection of hyperplanes. Okay, and your family F satisfies PQ property with respect to collection with respect to hyperplanes. Okay, then there exists C prime many hyperplanes. Okay, that will be a transversal of your.
So both the so when we go from points to hyperplane transversals, both the hypothesis becomes stronger. Now we are asking for more structure, and
Yeah.
and the conclusion is also stronger.
Stronger, but don't. So
What changes when we go from points to hyperplane?
So the proof actually is very similar. Interesting thing is hyperplanes have this very nice thing that we know is true. We have what is called hyperplane separating theorem, right? So convex geometry, okay, makes the proof easier. So by the way, not only for compact convex sets, this theorem holds for if your F is a collection of compact connected sets, then also this. At most C prime, many of them. hyperplane will be sufficient. So if your family satisfies PQ property with respect to hyperplanes, then your family can be transverse or pierced by at most C prime meaning.
But shouldn't it also, if you have C points, then you can just take one hyperplane to every point, would that not work? Like,
Yeah, sure. But I'm saying this is being satisfied for hyperplanes, not points.
I think the hypothesis also becomes.
So if you take now, let me just. So if you take hypothesis, so the hypothesis is now with hyperplanes. Your tau, if you remember, if your tau was like your PQ property was with respect to tau, tau along Gleitman was points. Here it is hyperplanes.
No, so the point is, both the hypothesis and the conclusion has become weaker.
what are different to the hypothesis?
Well, the fact that the single property with respect to hyperplane.
Not points.
No, so the question is, I think, taking Mrinal's question, so suppose I keep the hypothesis stronger as it was, so I keep points,
Yeah.
and I want to pierce by hyperplanes and not, so then do you get much better numbers?
No, I don't. Don't. Yeah.
If you get C points and avoid.
No, I'm just,
See, obviously, if you can hit with something with C points, you can hit that with C mini hyperplane.
yeah,
But
but
you want it to be much better numbers. One thing you see, one the obvious is whatever is the number of points required divided by D will be a number of hyperplanes.
yeah.
So that's the simple thing is already. But you want something more complicated. So few more things. So let's say F doesn't have to be even connected. Okay. So let's say your F is like so let's say your family F is collection of sets in Rd, compact sets in Rd, such that each of them is a union of at most k many connected sets. Okay. Then also this theorem works. And if this family satisfies PQ property with respect to the hyperplane, then you have a C prime that depends on K, P, Q, P. Okay. Again, all of these nice things, by the way, but connected set satisfying is not surprising also. Why is that? Because see, think if I rather than working with connected sets, let us take this convex closure of the connected set. That will also satisfy PQ property. The hyperplanes that intersects those convex sets will also intersect your connected sets. It's just hyperplane separating theorem. Okay, but this is something that happens quite a lot, by the way, in combinatorial geometry. Okay, so this is nice. I have seen people in the tutor here, like Jack Master is. Okay, so good. So
Finally you are getting it.
yeah. So one thing that happens is so in computational geometry as well as in what is combinatorial geometry. So here you want to do like come up with algorithms. Here you want to come up with like bounds. So this is like graph theory, and this is your algorithmic graph theory in the setting of geometry, right? So if you're working with hyperplanes, you have good algorithms, good bounds. If you're working with points, you have good algorithms, good bounds. Okay? When the codimension becomes more than one, then problem starts. So let's say the problem case will be lines in R. Okay? Lines in, and the thing is, points anyway is you can build a nice structure with points, but with hyperplanes, again with this hyperplane separating theorem, partitioning space with hyperplane, these objects can be used nicely to prove theorems, which you don't have for in between dimensions. So that the complicated dimension is when k is less than p minus 1 and greater than 1.
Greater than equal to 1?
Oh yes, sir. From lines to just below it. And same is happening here. It's not that. So, and this is what was noticed by again Alan, Kalai, Matosik, and Meshulam. What they showed was, can we have a PQ theorem for K flags? K dimensional affine spaces. So let's say your town now is all K dimensional affine spaces. Your family F satisfies PQ property with respect to this town. Can we have a PQ theorem for that? We don't.
Or it's impossible.
Yeah, there's an impossibility. And this impossibility has been they have kept improving and improving now, like not they, like other people of the world. Like even for very simple objects, this thing does not work. Like very simple collection of convexes also.
Sorry, I missed the inclusion. Why it is, if the K is here, then why?
So for points, you have this 9. So let's say you think of the point case. Okay, the point case basically boils down to doing linear programming, right? Hyperplane case, you have what is called hyperplane separating theorem, which are both are actually same thing looking from the dual angles, right? This works. These two sides, once I take care of one, most of the time I can take care of the others. In between, we don't have. A line in R3 is not partitioning a space. A hyperplane in R3 is actually partitioning a space. So I can like partition and work on the separate side and like have a kind of divider conquer or just partitioning technique. Okay.
But do you know that, I guess it's, so let's say there is a reduction that says that if it's true for K equals to 2, then it's also true for D minus 3.
No, I don't know. Don't know.
Duality also brings.
There is, yeah, so I don't know of any duality that like goes from like 1 to D minus 2 yes. Which is really interesting, right?
What's the point if I have a PQ, that's for any PQ.
Any PQ are always satisfied with this. So I am slightly lying, almost to this kind of a thing. So, but the Helly's theorem does not go for lines in R2 level. We don't have a Helly's theorem for lines in. Okay. If and again the problem that happens there is if you want to show exactly one line that goes through all of them, that is the problem. If you say you can hit with constant, and there is other sign is a constant, you just want it to be a constant but not one, then again you can recover things. How am I doing? Oh, okay.
70 minutes or so. Yeah, 70.
Sorry, okay. So, as with any area in CS, math, and once you get stuck with really hard problem, you try to do a generalization. Okay, because and this is what these people did. Okay, and I'm not saying it like a joking thing. So I found this very interesting. So what they said was, okay, so let's say F is an infinite collection of points. Okay, and so let's forget about this symbol. So the way to think about it is, so it satisfies the following property. Okay, that again we have tau, which is your collection of K flags. Okay, and your family F satisfies the following property is take F is an infinite family, take any infinite sub collection. Any infinite sub collection. Okay. Then from that sub collection, you will find Q sets that can be pierced by a single K. Okay. I say if I say for infinite, ideally you want to what all infinite, do it for countably, like the first infinite set we have. Okay. So the thing is, take a countable sub collection of take any countable sub collection of F. Okay. From then, from this family, you can find Q sets that can be pierced by one single K. If suppose the family satisfies this problem, and we still recover something like we do here.
So here, F itself doesn't need to be counted.
No, F is not counted. Doesn't have to be counted. Okay. but the subfamilies are countable. Okay, we have this Aleph not symbol, basically countable subfamilies is what we're looking at.
So, and there's no assumption of compactness or anything.
That's for the time we don't define it. When we prove mentioned result, those things will come. Okay, and so suppose the family satisfies this, what kind of results can we do? Okay, so this is the thing that Keller and
QK sets are again universally quantified, right? Like for all QK sets from you.
no, not for all Q cases. For all infinite countable subcollections of F, okay, there will always exist. Take any one of any for all this, I will find Q among them that can be used. So the way to think about is P if you have infinity, countable infinity, P, and Q remains Q, like we do. Okay. And they asked the following question. So they basically proved it that. Oh, sorry. So if your family, so let's say F. So let's say F is a collection. Forget about what I fact convex set. So F is a collection of nicely shaped compact convex sets. Okay. Very nice. Not too large, not too small. Okay. Both. Not too large and not too small. Okay. Convex sets. And it satisfies this infinite k plus 2 property. So like if I take any infinite subcollection, there will be k plus 2 sets in it that can be pierced with a single pair. Then the whole family can be pierced by a constantly many k pairs.
Wait, so the
Finitely many.
yeah, but this small r and capital R, they do not appear in Q.
No, it won't appear. Because I will, so I will, you will see why it won't appear in the later, just when I go to the next slide. For the time being, what I'm saying is, I'm not saying there exists a universal constant at any.
So the smaller, bigger was what you were saying, not too small.
Not too small.
So sandwich between
Sandwich between two
ellipsoids.
two balls with ellipsoids. Okay. And now the thing is, and I'm saying this family F, you can have a transversal of size of a finite size. I'm not even saying constant size. Like there is no universal.
Oh, it depends on R.
So let's see why even that is not true. Okay. Let's see. So let's say rather than R and fact convexes, let's think of them as let's say that they have proved this theorem for unit balls. Closed unit balls in R. Okay.
No, but I confused now. So, but how many K flats do you need to pierce?
I will only guarantee that it will be finite. I won't be guaranteeing, up till now I'm not guaranteeing anything else.
So if this not wasn't there, it would be trivial, I think.
If it is PQ, then those can use PQ. Even then it's not trivial, but okay. So for points case, we could have just got it from a hyperplane case. We could have got it from Alan Gleichmann or Alan Perles. I'm just saying finite.
It's not algebra. It's not algebra.
It's not algebra or any other higher infinity. Okay. Which anyway I don't understand. So, so
Base limits and one.
yeah. So let's see. So let's think of this theorem as rather than R at that, just think of them as closed unit balls in R. Okay. Good. What so they have proved this. Okay. So now the question becomes is, and actually they proved just in the conference version they proved this. Then in the I'm sure there's some in the journal or the updated version. What they have shown is the theorem holds for near balls. If you again don't want to define near balls, just think of them as arbitrary closed balls in RT, where the diameter is not bounded. Not unit balls. It can have, it is still closed balls, but the diameter is not bounded. Or you can do very small, very large, doesn't matter. It satisfies Aleph not k plus 2 property. Then the whole family can be hit with a finite size k terms. Okay. Well, so this QK, k plus 2 is in terms of this theorem is optional, right? Because any k plus 1 convex sets, I can hit it with one k flat, right? That's a trivial thing. So this is like just going one more. One more interesting thing is, see this QK does not depend on D. PQ theorems of Alon, Keller, when it is defined by aggregate P greater than equal to Q greater than equal to T. None of that is there. Just one more than the trivial thing that you need. Okay. Okay. So these kind of binary theorem is a family of thing that is now also being studied now. Again, all this Helly's theorem, Catherine's theorem, there's a two-hour theorem, all this like classical results, what is now called as a dimension independent or no dimensional version of this theorem. This is kind of a no dimensional version of this. When we call it a no dimensional version, when the capital, like in the condition, the dimension of the space where the objects lie doesn't come. Okay. So okay, so one answer question is, can we have a universal constant? But I said finite, but that finite is that number will be at most C, D, comma P, right? Like for PQ. And that we can easily see won't be the case actually. So let's say you have J, like you have intervals, unit intervals, disjoint intervals, n of them, right? And let's say I construct my family by taking infinite copies of J1, J2, J3, J4, right? So it satisfies Aleph naught, comma 2 property always, right? If I take an infinite subfamily, there will be one Ji that will be repeated at least twice, right? But this I cannot hit with n minus 1 points, right? So this universal bound of constant won't be this. So that will say fine. So even from now on, I'm sure I've made mistakes somewhere I said constant. It will always be this finite. Good. So now the natural question is, so I mentioned fatness, but let's say niceness. What was the assumption that the objects are like the theorem that proves almost like closed balls. So I mentioned near balls. Near balls are like basically it doesn't have to be convex, but the near balls definition is such that as the diameter of the near balls grow, it will look more and more like a cube. Basically, that is the definition. So this kind of a niceness assumption can it be removed. Okay. In this respect, like Jung and Powell actually proved it. So what they showed was, suppose F is a collection of compact convex sets in RT that satisfies Aleph naught D plus 1 property with respect to points. Okay? With respect to points, not see if I want to go for points, it should be 2. I'm ensuring D plus 1. I'm going one more, not one more, I'm going to like L kind of a thing. Okay? Then the whole family has a finite size part. Again, this is not true if you move away from points. You move away from points, it's careless. You can give explicit construction like this. So let's so maybe I should only say so maybe okay, so let's just define the colorful. So let's say now you have this as we had like for colorful Helly theorem, we had number of families. Now let's say you have uncountable families of convex sets. Okay, and this family satisfies the following property. So let's think in the Helly what we said that I have n of them, n is more than d plus 1. What do you want? If you have a colorful d plus 1 from them, okay, then they will be interesting. So if I collect from the union, if I take d plus 1 convexes where each of them come from separate family, and if they intersect for all d plus 1 couples like this, then there exists a family that can be hit with them. Okay. Something similar I want here. I want to have a countable collection of convex sets. Okay. Construct any infinite sequence of convex sets by taking one, at most one from each of them. at most. Okay. Then from there you will find few of them that can be, let's say, pierced by a tape. Okay. Then can we prove something similar, like a generalization, like infinite colorful generalization along the line of L, right? Let's forget strictly one for the time being. So I can give anyone interested will see. So let's do this. So let's do it. So what we can prove now is, so again you have this infinite collection of convex sets. Take any countable colorful subcollection. Okay. If they satisfies Aleph not K plus 2 property, okay, then and the convex sets are of nice shape. Nice shape in the sense condition. Okay. So like maximum radius of the maximum inscribed ball divided by the ratio, that is bounded. Okay, so the objects are nice shape. Okay, so more like me, think of it, the round kind of objects you are looking at. Okay, so but it can be, doesn't have to be like diameter is not bounded, just the ratio between these two has to be bounded. Okay, then what you can show is there exists, so you will always find a constant size K flag, constantly varying K flag that will hit all of these families except constantly varying. So you will throw away this constantly varying out of this infinite sequence, throw away some constant number of families. Rest will the whole union can be hit with this constant size. Again, it is exactly analogous to the lines of colorful Helly in terms of n minus k. Okay. There you will be throwing away at most d. Here you will be throwing away at most a finite number of families. Okay. And the rest, take whatever is left, take the union. The whole thing can be hit with finite number of things. Okay. Again, from here you can recover what Perles and forget Keller and Perles did. All of them. X are just repeat, then you get the whole Keller and Perles results. Okay. And it is for more general objects. Only thing is like for their near balls. Okay. Near balls condition that they have doesn't have to be convex. Here convexity. So we can show that convexity cannot be relaxed. Okay. Only generalization we can think of that we have done is the convex sets can have like the rounded convex sets it will work. So Jung and Powell also have like an alternative proof again with their different framework. They were alternative proof for this. So maybe I just slightly. So this is basically the convex. So if you assume that your compact connected set have good condition number, but you don't assume them to be convex. The previous result. And if anyone is interested, I can take this study on your time. But I can show you the construction is very easy. It's not very hard to show. Okay, so let me just skip. So we'll take the. Okay, so see if you remember, like I was asking this question that can there like what Keller proved was for convex sets that are of the form like unit balls. What we showed that there don't have to be unit balls, should have bounded condition number. Then they have also near balls also is good enough. Okay, but like can this condition be removed in general? Okay, if I want to prove an Aleph not K plus 2 property. Okay, and this is a very easy construction to show that you won't be able to do it. Okay, and one way is just by just doing like high school. What was high school? Yeah, like what we did for like circles and tangents that we did. Okay, so let's say I have this quarter of a circle. Okay, and I'm just looking just do this. Okay, and for each of these points, okay, let's construct a segment that goes from here to here. Okay, and my set, what are my sets? For each angle theta, I have this segment S theta. Okay, So my family F is collection of S theta, where theta is between pi by 2 and 0. Right? Any pair of them are intersecting. But the whole family I cannot treat with constantly many points. Because each point can pass through at most 2 tangents. Okay, and now you can make them rectangles, you can have an area. So this is like but intuition is there. Then you can show okay, it does not do segment, you can make it rectangle. The rectangle, the rectangles are not axis aligned, then also this doesn't work. So what let's so we did for K plus. So let's now just finish it with the main results. We'll skip this. So the main theorem that we can prove again is the final one I want to share is so again you have an infinite collection of convex sets, and if you take any countable subcollection, let's say, okay, you will find D plus 1 sets that can be transversed by a single vector. So this is a condition you have. Okay. For the point case, you have if I take infinite subcollection, you will find D plus 1, which are there is a point that lies on all of D plus 1. Here is a hyperplane that goes through them. Then the whole collection can be hit with finite unity. Okay. This, by the way, theorem is actually of the form K plus 1. Right? K here is D minus 1. So for arbitrary families of convex sets, as long as K is D minus 1, you don't need any conditions on you just need connectedness, compact connectedness. Even then, you can even further generalize and say at most K many connected components. Okay, and then it will go. Okay, and again, this argument is because of that 4 nice properties that hyperplanes have. Okay? That makes it good. You can in Powell also, and they have an alternative proof for this one. What we showed was we can prove a colorful variant of this. Okay. So maybe I'm already overshot. I wanted to give a proof of one result, but maybe I will take it. Thank you for attending.
Questions?
The point hypothesis that you have for the PQ theorem. So can you have it for the spherical geometry or Poincare model?
So spherical geometry. So something similar you can prove for what are called cap sets. So these are like okay. So I can tell you it's slightly a technical thing, but some similar things you can do for subsets of points on the sphere. But again, you cannot go very far with this. Again, you need some additional conditions.
Okay, and what about the Poincare model in hyperpolation?
That I have not checked actually. The Poincare model. So that I have to check whether it will work or not. Okay. So spherical geometry, there is something you can do. For capture this one. But not investigated. Maybe you can do something.
What about finite fields?
So convexity defining for finite field, I don't. You should go math department. The whole area, those that is there.
Right, like you need order.
Huh?
How do you find convexity defined?
Supposedly there is a way of defining fundamental group for varieties or finite field. When I hear this, I just don't understand. Supposedly there is something. I did a reading course some time, but now I remember nothing.
Is it meaning you taught it or you?
What would that be for?
Like, there has been ordering.
Yeah, I mean, that's what I'm saying. They have some kind of a topology you can put on these objects.
On what?
On this, like let's say varieties over finite fields, you can put on.
But like, how do you get convexity?
You don't need convexity, right? You need contractibility. Oh, so then, homotopy, but homotopy, suppose the homotopy doing is a very more difficult than just fundamental group. Fundamental group is supposedly.
What is conductivity? Simple calculus or more?
We can, so any, so simple connectedness is also good. Any curve can be connected.
I mean, Theorem is something also used for the Sylvester-Gallai like configurations and so on. And Sylvester-Gallai theorems have many
Finite.
approximate versions.
Yes.
Are there analogs of that here?
Here we have analog of it, which is called fractional.
Oh, okay.
Yeah, so the thing is, what one thing that we were thinking here is like, can we have a fractional? So there is also fractional PQ theorem. So there is like non-linear course in PQ theorem, so like you can do color. I define this PQ theorem. You can do a colorful PQ theorem, and then you can have a fractional PQ theorem. Okay, fractional version. Okay. So the I will tell you the fractional Helly theorem. That one. Okay. So what is fractional Helly theorem? So I am looking at all D plus one tuple of D plus one subset. I want all of them to be intersect. Right? There is a, let's say, alpha fraction of them is. Okay. Then you can hit it with as a function of alpha. Then there's a very nice behavior actually. I don't know. I say it's something like one. How many you need? Maybe I don't know. I like this. I will check. Go and check. But there's a very nice series that will. And similarly, you can do for.
Any theorem proof is quite simple, but these fractional versions are also.
Which one?
Any theorem proof
Yeah.
is actually very simple.
Very
But the fractional.
Slightly more complicated. Okay, so but not much. We teach in course. I mean, those have been like simplified over time. Now there's a very nice book. Combinatorial convex geometry by one of the leading figures in the field, Emre Barani. So we used to can have a look. It's a beautiful book. All chapters are like 4 pages. So very nice, very elegant full set.
Any more questions? So that's that one. Other kind of